Hello, today is logs day 1. It's actually logarithms. We shorten it and call it logs. I'm going to first start out talking about inverse functions. We haven't talked about functions in a long time, but we just finished up exponents, and logarithms and exponents are inverse functions. That means that they undo each other. Like addition and subtraction are inverse operations, multiplication and division are inverse operations, squaring and square rooting, and then now we're going to have exponents and logs. Okay, so let's start out by looking at what we have here. So inverse functions. The inverse of f of x equals e to the x. Remember we talked about e to the x is just a number raised to a power, because e is a number, like pi, it's an irrational number. And when we graph it, over here it's the blue line, y equals e to the x. The way we find our inverse is by reflecting it over the line y equals x. So that's what I did here. It's the graph line y equals x, and when you reflect over it, you go the same distance away. So it's taking and folding on this line, and you get your mirror image. And the inverse for e to the x is the natural logarithmic function. We call it ln x. I know it's natural log, which should be nl, but we label it as ln. And you can usually find that button on your calculator directly below the log button. But since f of x equals e to the x is a one-to-one function, you know that the inverse will also be a function. One-to-one means it passes the horizontal line test. But what is the equation of the inverse f of x equals e to the x? Well, to solve for the inverse algebraically, this is something that we're going to learn how to do in this unit. We set the equation equal to y, we switch x and y, and then we solve for y by rewriting it in log form, which is what I'm going to show you how to do later today. And when we have a log and the base is e, it's also called the natural log. Inverses for other exponential functions are found in the same manner, and I'm going to show you what that means as well. If you look here, on the graph we had the point 0, 1 right there. And if you notice, every time we did an exponential function, it went through this point 0, 1, unless we had the graph move. Now, when we switch it to the natural log of x, we switched our x and our y. Like we did over here, we switched x and y. And if you look at it, this point now becomes 1, 0. So again, we switch x and y. And then that becomes my new point. Okay. Now we have other exponential inverses. If I have the graph y equals 2 to the x, the inverse is y equals log base 2 of x. Again, set the equation equal to y, switch x and y, and then solve for y by rewriting it in log form. Again, I will show you how to do that, I promise. But it's just kind of neat how here's our exponential function, and then here's our logarithmic function. And here's a reflection of the line y equals x again. Now we have a fraction, okay, 0.5, remember, is equal to 1/2. So this is y equals 1/2 to x. You want to look at it that way. Again, if I want to find the inverse, I switch x and y, and then I solve for y. But this graph looks a little bit different than the other two. It's a little bit harder to see the inverse. But again, if you fold this on this line y equals x, the red will then become the blue over here, and this red will then become the 3 over here. Remember, when we have a fraction, our graph is decreasing. And here just shows us another way of solving this algebraically. We're not going to get to that for a couple of days, but we will eventually get there as well. So, let me, next page here. The definition. Okay, the definition, we have the logarithmic function is the function y equals log base b of x, where b is any number such that b is greater than 0, b is not equal to 1, and x is greater than 0. Y equals log base b of x is equivalent to x equals b to the y. The function is read log base b of x. So let's look at the logarithmic function. If you notice, some of these numbers we were working with on our graphs for exponential functions, before we had our x values of -2, -1, 0, 1, and 2. And a lot of you asked me those numbers that we use to graph. The answer is yes, that makes it easier for us. But now look at my x values, 1/4, 1/2, 1, 2, 3, 4. If you notice, the x and the y have just changed places. Okay? Something that you need to be careful of when you're dealing with logs, this is true. X must be positive right here. This value has to be positive. Most logarithmic graphs resemble the same shape. Resemble this shape right here, and it appears to be increasing. This graph is very, very close to the y-axis, but does not cross it. The graph increases as it progresses to the right. Okay? And a straight line, the rate of change remains the same across the graph. In these graphs, the rate of change increases or decreases across the graph. We talked about that with the exponential functions as well. Some characteristics of the graph. Okay. Some characteristics we have here. We are in the form of log base b dx. There's certain things that will happen. The graph crosses the x-axis at 1, 0. When b is greater than 1, the graph increases. When b is a fraction, the graph decreases. The domain is all positive real numbers, but it's never 0. The range is all real numbers. Now, if you remember when we talked about exponential, these two things were reversed. The graph passes the vertical line test, therefore it's a function. And the graph passes the horizontal line test, which means its inverse is also a function. This is the one-to-one. And the graph is asymptotic to the x-axis, which means it is very, very close to the x-axis, so it does not touch it or cross it. We have the natural log function, okay, and this is where we use ln instead of this log. Remember, our base is e, and e is the irrational number. We talked about this in the last unit. E is 2.718288183, and it's named after the Swiss mathematician Leonhard Euler. Remember, it looks like Euler, but it's pronounced Euler. The characteristics of this graph are similar to the ones above, so this is just simply a special circumstance or special case of a log. Okay? So let's just solve some problems. Try to do something. Well, what exactly is a logarithm? We really didn't say what a logarithm is. I just told you we'd be working with something that's the inverse of an exponential function. But a logarithm is an exponent. Nothing more, nothing less. It is an exponent. Okay, over here, I'm going to write some stuff down. Okay, my friend Ben and his log time pal I call this unit. Okay, Ben, you can see it's spelled Ben. B is the base, E is the exponent, N is the number, and it's log time pal instead of long time pal, B, because it's log base B of N equals E, which is the exponent. That's why a log is an exponent, because it's equal to E, the exponent. So B me, and that. That sounds kind of silly, but I have found over the last couple of years when I've used this that it is very helpful for people when they're actually solving the equations and going back and forth between exponential and logarithmic form. This is the way that we do go between the two forms, and we have to convert them. So, for number one, write the equation of 9 to the, it's really hard to see it, but that's supposed to be the third power. Looks kind of like a second, but it's not. 9 to the third is equal to 729 in logarithmic form and express its meaning in words. Well, what we need to be able to do is identify what B, and N are. As long as we can identify B, E, and N, we can go back and forth between the two forms. My base is whatever's being raised to the power, and my base in this case is 9. My exponent is the power, which is 3, and my number is the other number over here, so 729. So I need to put it in logarithmic form, which is this form right here. So I'm going to say log base 9, and we draw a little 9. It's supposed to look like a subscript, and my number is 729 equals my exponent, which is 3, because a log is an exponent. And to put this in words, would be the exponent to the base 9 of the number 729 is 3. Okay. For number 2, write 3/2 equals log base 25 of 125 in exponential form. This time I'm taking a log and putting it in exponential form. So again, I need to identify B, E, and N. For number 1, I took a Ben, which is exponential form, B, E, N, and turned it into beanie, log times Ben, B, me, okay? This time I'm taking the beanie and I'm turning it into a bend because I want it to be an exponential form. My base is always the subscript or the smaller number, so it's 25. This is the number portion, which is 125. And the log is always equal to the exponent, which is 3 over 2. So now I'll put it in exponential form, bend form. My base is 25, my exponent is 3/2, and my number is 125. And then you take a quick little mental check after the bend form. The square root of 25 is 5, 5 cubed is 125. This needs to be a true statement. If this is not a true statement, then you converted it wrong. So you can always check to make sure that you put it the right way. For number 3, find the value of a when that's log base 8 of a equals 1/3. If I'm in logarithmic form and I'm trying to figure out a missing part, I need to take it and turn it into a bend form. Okay, I'm going to put it into bend, exponential form. My base is 8. My exponent is 1/3. My number is what we're looking for. So I have 8 to the 1/3 equals a. Well, 8 to the 1/3, that is another way of saying cube root of 8. So a is equal to 2. As you can see, logs and exponents are related and they go hand in hand. Solve the following equation for x. We have log base 2 of 1/9 equals log base 2 of x. Actually, this should be log base 3. It's a target point. Sorry about that. So log base 3 of 1/9 equals log base 2 of x. Well, what we're going to do here is we're going to kind of separate this problem. We're going to look at the left side and then we'll look at the right side. On this side, I need to get a number. Well, the only way for me to get a number is for me to turn it into the bend form. So b equals 3. E is equal to, we don't really know. So we'll name it a variable, and since we're solving for x, I'll use the variable y. And n is the 1/9 portion. So I'm going to put it into a bend form, exponential form. So 3 to the y equals 1/9. Well, we just solved these equations. Picture bases to be the same. So 3 to the y equals 1/9 is the same thing as 3 to the -2. So that means that y equals -2. So that means in place of this right here, I can put my -2. So I would rewrite this as -2 equals the log base 2 of x. So now I need to find x. I need to put it into a bend form again. We're doing bend times 2 here. Exponential form. b, my base is 2. E, my exponents with the log is equal to, so that's -2. And n is what we're looking for. So my base is 2. And then -2 is equal to x. Well, 2 to the -2 is 1/2. Okay, so 1 over 2 squared, so it's 1/2 squared and 1 over 2 squared. So this is 1/4 equals x, and that's what we were looking for to begin with. Now I know that is the end of your printed note. However, I want to go back over graphing, so I'm going to add another page here, and we're going to graph y equals 2 to the x. So we just did exponential graph. So we always start with -2, -1, 0, 1, and 2. 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 to the second is 4. So at -2, we have 1/4. At -1, we have a half. At 0, we have a 1. At 1, we have a 2. And at 2, we have a 4. Okay. So this is y equals 2 to the x. Now, some things that's going to remind us when we have an exponential function. With our basic exponential functions in this form, we are always in preference 1 and 2, whether they're increasing or decreasing. In this form, in the general form, it's always through the point 0, 1. And then it said if b is greater than 1, it was increasing. And if b is between 0 and 1, which is a fraction, it was decreasing. Okay, that was important information before. My domain is all real, okay, numbers. And the range is y is greater than 0. Remember, domain is our x values, range is our y values. Okay? Now, we're going to graph a logarithmic function. Color here. So, for the inverse, is always switch x and y. And our graph always reflects over the line y equals x. Okay. Alright, what we need to do is look at our chart when I say we switch x and y, I mean we literally are going to reverse our x and our y. So our x's were negative 2 through 2. Those are now going to be our y's. Okay? So that's negative 2, negative 1, 0, 1, and 2. Now my x's will become 1/4, 1/2, 1, 2, and 4. I want to go ahead and graph this. I have 1/4 negative 2. And then I have 1/2 negative 1. And then I have 0, 1. And so to see that I will have 1, 2, 1, and then 4, 2. So 2, 1 here. And then 4, 2 is here. Remember, it doesn't actually cross the y-axis, so you come up really close to it. And then I'm going to take it up like this. Well, this is y equals, we don't know yet. We now have to write an equation. So, let's do this. We're going to write our equation. Before we had y equals 2 to the x. In our chart, we literally switched x and y. So x equals 2 to the y. Now, I can't leave y in my exponent. So what I need to do is take this and turn it into a beanie form. So my base is 2. My exponent is x because there's y. That's my exponent here, right here. And n is my number, which in this case is x. So let's put it into logarithmic form. That means I have to log base 2 of the number x equals y. So that's my equation, y equals log base 2 of x. And if you notice, if I were to graph the line y equals x, okay, that's, oh, that's line that splits everything in half. My x in my quadrants in half. And line is y equals x. It is a reflection over that line. So there are some things we talked about with the exponential functions that we can talk about with the logarithmic function. Okay, logarithmic functions in the basic form are going to be in quadrants 1 and 4. My green line is 1 and 4. And these in the basic form always goes through, instead of 0, 1, it's 1, 0. If b is greater than 1, it is increasing. And if b is between 0 and 1, it is decreasing. Okay, one other thing we need to know is our domain is going to be x is greater than 0, and our range is all real numbers. Remember, they're inverses, so they switch, which means their domain and their range also switch. So my domain for an exponential is all real numbers, therefore my range is all real numbers. And in an exponential function, my range is y is greater than 0, so my domain for my logarithmic function is x is greater than 0. Just because we switch the x and y places doesn't mean that the x and the y values actually change. The domain is always going to be x, the range is always going to be y. The domain is still x, the range is still y. We've just switched their values in those places. Okay, sorry that this was a little bit long, but I wanted to make sure that I explained it as best I could and showed you everything I needed to. Monday in class, we will go over some practice problems, and we'll be working on these. And Monday night, we have another video of the log A2. Alright, thanks for sticking it out, and I will see you in class.